Topic 5: Viscosity, Flow, and Specific Gravity by William, Mitch, Blake, and myself, Ethan. What is viscosity? Viscosity is often defined as the thickness of a fluid, but in reality, it is the rate that the fluid deforms. Viscosity is very dependent on the temperature, pressure, and the system being used. Some liquids cannot flow at all at lower temperatures. How viscous a fluid is can be measured by using a viscometer or rheometer. Viscosity usually isn't labeled on common household items because the rate that molasses or ketchup flows isn't vital. Viscosity is found on motor oils and other mechanical process fluids, where its deformation rate is detrimental to the engine's performance and its longevity. What is flow? Flow is a characteristic of a fluid in motion. Both gases and liquids are considered fluids, and when forces are applied to them, they can flow. Flow is used in many different industries, from aerodynamics to hydrodynamics. Flow can be used to find the speed that an engine is consuming gas, or how long it takes for a resolver to finish draining. What is specific gravity? Specific gravity, also known as relative density, is the ratio of the density regarding a substance in comparison to its zero point. In most cases, the zero would be water or air, but vary based on the situation. The specific gravity of something is extremely dependent on the temperature and pressure of its surroundings, as a higher temperature will make some fluids flow faster, and a colder temperature will make some fluids flow slower. Specific gravity is often used to see how buoyant something will be, as it is extremely easy to compare the known fluid to the unknown. To find the specific ratio of two things, use the formula specific gravity equals substance divided by reference. Purpose of the lab. The purpose of this lab is to expand our knowledge on what flow, viscosity, and specific gravity are, how they influence each other in a real-world operation, and to develop a comprehension of how they operate. What you will need to complete this lab. 3 different liquids. We chose gasoline, water, and liquid detergent. 3 mason jars. All ours are 1,000 milliliters. A funnel. We had a funnel with a plug for more accurate readings. A scale. And a big jar or bowl to catch the liquid from the funnel. Intended lab activities. The goal of this lab is to view the relationship between the weight of the fluids in the jar and the speed at which they flow out the funnel. Step 1. Find the weight of each liquid by using the scale. You can measure the empty jar, then the jar full of each liquid, then subtract the weight of the empty jar. Step 2. Find specific gravity of each liquid using the formula specific gravity equals substance divided by reference. Step 3. Pour each liquid into the funnel and record the time it takes for the liquid to flow out the funnel.
Alright guys, so how we're going to start our experiment real quick is we're going to take our empty jar and just get a weight on that. So once we have that, we can now subtract the jar weight from all the other jars, so we just get the pure liquid weight. So each liquid is going to be weighed. You're going to take your water first, so we'll get the water and get the weight of our water in the jar, and then the weight of the liquid soap here. And then as you're taking these weights, you're going to be recording each weight so that you have all 3. This is the gas here. Perfect. So now we have all 3 weights. I've already pre-recorded everything. So this is the point where you take the weights of each of the jars and subtract the weight of the glass jar to get your liquid weight. And then your liquid weight you could use to find the specific gravity. The base specific gravity is water, so we have the first one already, and that's 1. But you're going to use the weight of the detergent, soap, divided by the weight of the water to find the specific gravity for the detergent, and the same thing with the gasoline. And then our next step is we're going to determine flow rate. So here you can kind of see by the viscosity of each of the liquids what's going to flow faster or what's going to flow slower. But we're going to actually time them. In this step, you're going to need a jar with some kind of funnel, and I'm using a plug as well, so I can pull the plug and we can get a true reading. It's much easier than pouring it in. There'd be different pressures and things like that. So we're going to start with water first. So you're going to take your water and you're going to pour it in there gently. Perfect. So this is the point where your partner would need to have a stopwatch or on his phone even, where he's ready over here. As soon as you say 1, 2, 3, pull, he's going to start the stopwatch, and you're going to go until the level is through the bottom of the funnel. We're not going to let it drip or anything like that. It's just going to cause more time, and it's going to be infrequent. So here is your water sample here. You would stop as soon as it hits the bottom of the funnel. You're going to do each liquid 3 times because we found that the first time there could be room for error, especially human error, in the stopwatch and in the pulling of the plug. So here we go. Put the plug back, and then this is where you would run the water 2 more times. But we won't. We'll just put this back in. Go. And then this is the gas here. And you go 1, 2, 3. Your partner would start the stopwatch, pull. Want to flow out. You would record the time on that and do that once again 3 times. In between, I would recommend washing the funnel as well, because you're gonna have gas, soap, all kinds of things in the mix. There we go. Fix our plug. And then lastly, our soap. There we go. And then once again, 1, 2, 3, pull. Allow it to drain out. As soon as it hits the bottom, stop the stopwatch. And then you would do each liquid 3 times, like I said, to remove any human error. Once you get those 3 times, you would then add all the times together of each liquid, divided by 3, and then you'll have your average time. So that would be the best flow rate to use for this situation. Then you'll have all your numbers that you can use in all your equations to figure out the rest and to make your chart. All right, thanks guys.
So now time for our results. Weight results. The weight of each liquid was found by subtracting the weight of an empty jar from the weight of the liquid and the jar. So we found that the weight of an empty jar was 388 grams. The weight of the water and the jar was 1,363 grams. So we took our 1,363 grams, subtract the weight of the empty jar, which was 388 grams, to find a water weight of 975 grams. We did the same thing for detergent and gasoline to find a detergent weight of 1,015 grams and a gasoline weight of 724 grams. Specific gravity results. The specific gravity of water is known as our base and results in a specific gravity of 1. So using the formula specific gravity equals substance divided by reference, you can find the specific gravity for gasoline and liquid detergent. So for our liquid detergent, we just took our weight of our detergent, which was 1,015 grams, and divided it by the weight of the water, which was 975 grams, to get a specific gravity of 1.04. We did the same thing for gasoline to find a specific gravity of 0.74. Now for our flow rate results. Flow rate was found by timing how long it took each liquid to flow out the funnel. So as Mitch said, we're going to do 3 attempts, and then we're going to take the average time to find our flow rate. So for water, we found an average time of 2.49 seconds. For detergent, we found an average time of 4.16 seconds. And for gasoline, we found an average time of 2.24 seconds. As you can see from the information gathered above, as the specific gravity and the viscosity of the fluid goes up, it affects the speed at which it flows through the funnel and into the process jar. The same could be said for the weight, but the specific gravity is a result of the fluid's weight. Gasoline is the lightest and least viscous liquid, so it flows the fastest. Detergent is the heaviest and most viscous liquid, so it flows the slowest. We also realized water and detergent are very similar in weight, and gasoline is much lighter, but gasoline and water have very similar flow rates, and detergent is much slower. Thank you guys for listening. I hope you enjoy our lab.